LDA, that integration method for some boundary of that plane figure, which is not giving us that help of subdividing it in some general standard element shapes whose centroids are already located or known very simply. That is, if the boundary is very simple straight line boundary, we can subdivide in different components with known or very simply calculated location of the centroids. That also we can do. And some standard shapes like this were considered. A circular arc of central angle alpha is location of the centroid which is along this line of symmetry. For our convenience, we place that line of symmetry along the x-axis, and this is the calculation, and twice r divided by alpha sine half alpha. And we utilize this thing for calculation of location of the centroid for a sector of a circle. Okay, and there this is the element at variable location at distance r from the center, whose this width very small, infinitesimally small, this is dr, and there dA is equal to r alpha dr, and express this integration, expand it, integrate for this limit 0 to capital R, we get 4r by 3 alpha sine half alpha. Actually, it should be 4 capital R. Okay. This is capital R. Now next, another method we discussed, that is considering this triangular element. For this triangle, its base is r d theta, and d theta angle is very small, infinitesimally small. So height of this triangle is simply this capital R. And location of the centroid is at 2/3 distance along this line of symmetry. That means at 2/3 R. So x coordinate of that centroid is that x coordinate of the element, that is 2/3 r cos theta. You do this calculation, you get 4r by 3 alpha sine half alpha, that same expression. Then we consider several simple boundary situations like this one, and we subdivided in two rectangles. This is 1, this is 2. Correspondingly, the location of the centroids we considered. Here it is C1, C2, and these are at half distance along x-axis, half distance along y-axis for this location. For this C2, you have to consider in this way. This part is fixed 1 inch. This part is half of 3 inches. Okay, so this type of small calculation you can make, find A1, A2, find X1, X2, Y1, Y2, fill it up those in a table, make two additional columns for these products A1, X1, A2, X2, and A1, Y1, A2, Y2. These are like this, and you can do this thing very simply. Now here is a problem where we subdivided in this direct way, 1, 2, or you can do in some different manner also, where we consider the full rectangle, and from that we subdivide this part and this part. So that is not at such a difficult thing. Okay. Now that subtraction of area, it will give you simply the change in that sign for those parts where A1, A2, or A1, X1, A2, X2, or A1, Y1, A2, Y2, those calculations are there, and fill it in the table with proper sign. Here we have a little, not difficult as such, I would say. We think it in some different manner, plus or minus Now, in my opinion, if we subdivide in this way, then it is 1, this full rectangle is 2, and this triangle is 3. At 1/3 distance from the base, at middle, and at 1/3 distance from the base, somewhere here, these are C1, C2, and C3. And what about area A1? Half. Height is 30 millimeter. Base is 54 plus 72. A2. Length is 54 plus 72 multiplied by this height, 54. And what about this third component, A3? Half. Base 48 multiplied by this height, 72. Units are in millimeter square. Okay. Now for C1, what about the value of XC1? This much. This is 2/3 of 54 plus 72. That is from here to here. That minus 54. This is XC1. You can think it in some different manner also. That is distance from this base. It is 1/3 of 54 plus 72, and subtract it from 72. So 72 minus this will be XC1. Similarly, these calculations you need only to concentrate properly, and without any mistake you write down those expressions. Even if it is little longer expression, nothing to worry. But if you go for some mental calculation and put the final value, if by chance there is a mistake, so throughout the solution it will carry forward and error will be accumulated, ultimately giving some impractical result or which is not expected. Anyway, so you can subdivide in some other way also, and that experience you can get from your practice. So there is no easier option, and you need to do that practice. You have to provide the time. Now what you can do, we can even consider this full rectangle minus this part. So this multiplied by this area, suppose it is A1, then minus this A2, and similarly here we have that centroid, XC1 will be negative and YC1 will be positive. In this case XC1 will be positive, but what about YC1? Sorry, if it is 3, or normally we write it as Y3. It is negative 1/3 of 48. So all such small things, but very important, you must keep it in your mind and do the things, prepare that table, and it is a very good hunting ground to score marks. Next problem, here is also that straight line boundary is very easy, but one thing is there. For this case, the origin was given, x-axis, y-axis were positioned properly, but here it is not given. So Sorry, it's given, but origin is not written. You should write the origin O here, and with reference to x-axis and y-axis, you have to find it. Now, if by any chance it is mentioned that origin is not here and these are not x-axis, y-axis, instead of that, the x-axis, y-axis are mentioned at some other location. Suppose this is the y-axis, this is x-axis, and this is the origin. So here also you can subdivide in two suitable or convenient components. One is for the smaller rectangle on the positive side with reference to x-axis, and other is the triangle. So what about A1? A1 is 6 multiplied by 3 inch square. And what about A2? Naturally, it is half multiplied by 6 inch multiplied by 6 inch. A2. Then what about X1? X1 is half of 6. Y1 is half of 3. What about X2?
Sir, it's half into 6
Sir,
into
why
12,
it was half
sir.
into 6 into 6?
Into 12,
It should be
into
half
12
into 6 into 12. Yes, sir, 12.
Yes.
in A2.
Thank you for going through these calculation steps. Okay, and please believe me, intentionally I have not left a wrong thing there. It was my mistake, and thank you for correcting me. Now what about x2? X2 will be 1/3 of 12. 1/3 of 12 is this much. And what about this length? It is 6. So 6 minus 1/3 of 12. In other way also you can find, that is 2/3 of 12 minus 6. This is 2/3 of 12. From that you subtract this 6, you will get the same result. 8 minus 6, that is 2, and here also it is 6 minus 4, that is 2. So only thing you need to find out these values correctly. A1, A2, X1, X2, Y1, Y2, in that table, in those columns, the product's area multiplied by the corresponding location of the centroids, A1, X1, A2, X2, A1, Y1, A2, Y2, put the proper sign, get the algebraic summation, and at the bottom of the table, you find 3 algebraic summations and find the ratio. Summation A1, X1, summation AI, XI divided by summation AI, that is the XC, and summation AI, YI divided by summation AI, that is YC. Correct? Now, we can take up some more such situations having either straight boundaries of very standard values, x-axis, y-axis located or defined properly, or it may be a pure curve, or it may be a combination of straight boundary and curved boundary. But whatever it may be, you need to subdivide the whole thing in suitable components where you know the location of the centroid for these components. Okay, so if we have this problem, then for the curved part, that is 1/4 of a circle, so we can consider it in this equivalence. One thing is this quarter circular sector, From that, you subtract a square of sides 5 inch, 5 inch, and radius of the circle is 10 inch. Next, you need to find out the individual centroid. Now, what about the individual centroid? Individual centroid is along this line of symmetry and at how much distance?
So 2 root 2 r by pi.
So radius is 5√2, no?
And yes, so into r will be
4r by 3 pi. And here, you know, half of 5 inch, half of 5 inch along positive x-axis, y-axis. Now, what about this distance for x1 and x2? Other
45 degree 4r by 3 pi into by
this
root
is 4r by 3 pi
into 1.
multiplied by cosine 45 degree. And what about this y1? 4r over 3 pi multiplied by sine 45 degree. Now you can simplify this expression, but you need to start from this basic. After this distance is you are getting from your known values. So if in any problem for examination you are asked to find out the location of the centroid, you have to find out that location. Otherwise, if nothing is mentioned, directly you can assume this value 4r by 3 pi, but that is valid for this circular quarter circular sector along this line of symmetry. If it is of any other value, it will be different. So general formula you have to remember 4r divided by 3 alpha sine half alpha. Okay. Now, next thing, once you have that known components, it is very simple. The known boundary of curved line, known boundary of straight lines, these are very easy. And you can attack all these problems without my help. Now, if we consider another one here, it is a symmetric figure. So even some
Sir, one confusion is there, sir, in the previous one.
where?
Sir, in the previous example.
Oh.
Yes, sir, here. Sir, actually, sir, here the angle is 90 degree of the quarter sector. So if we apply that in formula, then it will be 4r by 3 into pi by 2 into sine of pi by 4, no, sir? Because the angle is 90 degree.
What about this distance?
Sir, 8r by 3 pi for this figure, sir, for 90-degree case, sir.
This is 4r divided by 3 alpha multiplied by sine
Alpha by 2.
alpha by 2, that is 45 degree. 1 by root 2. Okay, you do the calculation, and for 90 degree, whatever value you are getting, you have to take that only. So if you find any mismatch with any values, so please correct it. But method, that is, you need to find out the location of the centroid along this line of symmetry. That is this much. This is 8r over 3 pi multiplied by 1 over root 2. That is 4 root 2 r divided by 3 pi. Okay. Now after that, 4 root 2 divided by 3 pi multiplied by r, and this angle is 45 degree. So 1 over root 2 you need to multiply with to get the x coordinate, x1, and it will simply cancel out root 2 terms from numerator and denominator. So it will be 4r over 3 pi. So x1 is 4r over 3 pi, and y1 due to symmetry that will also be 4r divided by 3 pi. So thank you for correcting. Okay, and this length you do it according to this calculation, or one simplification that you can do, that is, if we consider a semicircle, its centroid at this much distance. So if we consider it subdivided in two different parts, one is the upper one and other is the lower quarter circle, then for this individual quarter circles, the location of the centroids will be along this line. One will be here along this 45-degree line, other will be here along this 45-degree line. And those x1 or this x2 or this y1 or y2, they will be this value 4r divided by 3 pi. And this length will be that divided by sine 45 degree, that is root 2. So 4 root 2 r divided by 3 pi. So naturally, that mental calculation, definitely there is some possibility of sources of error. So you do it with full detailed steps, not like me. Okay. Now next thing, we are talking about this problem here. The perfect symmetry is there. So xc will be 0. Now what about the components 1 and components 2? That we consider in this form. It is equivalent to this rectangle minus this semicircle. Okay, so if it is 1, if it is 2, then actually its centroid is at a distance of how much? 4r divided by 3 pi from top. So it will be 3 inch minus 4r divided by 3 pi. Okay, this will be y2. And what about y1? Y1 will be at the middle, that is half of 3 inches. So with these hints, now everything is ready in your hand. Now we come to another situation where the curve is not like this circular arc, where that x square plus y square is equal to r square, that equation is not required. Simply its known values 4r divided by 3 pi or 4r divided by 3 alpha multiplied by sine half alpha, all such things are known. But for this case, it is a second degree curve. And for this second degree curve, the equation is y is equal to kx square. Now, if it is, if you try to remember, is it not something like the equation of a parabola?
Yes, sir.
What
Yes,
about
sir.
the axis?
The axis will be x is equal to 0.
Y equal to
Axis is y-axis, positive y-axis. toward the opening of the.
Yes, sir. X equal to 0.
Okay, and a vertex is 0. What about the focus?
K by 4 comma 0.
Normally we are
0 K by
normally we are convenient with these equations. Y square is equal to 4ax or x square is equal to 4ay, and make those equivalents here.
K by 4, sir.
Okay, k by 4. So that
Sorry, sir. 4 by K, sir. No, 1 by 4.
y is equal to 1 by 4a x square, and k is here 1 by 4 or such kind of thing. So what about a?
1 by 4.
1 by 4k.
So a is 1 over 4k. So that kind of equivalence you can make, or directly you can use this expression. It is a second degree curve, and depending on the value of k, you can find it. Suppose if k is equal to 1, in that case, y is equal to x square, isn't it? And
Yes,
when
sir.
you have y is equal to x square, or x square is equal to y, in that case, focus will be, focal distance will be 1/4 from vertex to focus. So all those known calculations, the result, etc., what you know from your school coordinate geometry, those will be very much helpful for this situation. But our intention to find out the location of the centroid for this sector. The sector is formed by 3 boundary lines. Hold a minute, beta. Now come back to the discussion. Now what about the boundary lines? A straight x-axis, a straight line parallel to y-axis at a distance a, and this is the curve whose equation is given by y is equal to kx square, right? Now how to find the value? Now just before that, it is not indefinite like this. This boundary mentions the area which we need to consider for calculation of the location of its centroid. So naturally you need some stop line. So this is that stop line. Now at this location, what about the coordinate?
A comma B.
It's very simple. Next, what we do, put it here in this expression. So B is equal to K multiplied by A square. So from that we get the value of K. K is B over A square. Done. So that is the first step. And second step is not that calculation. Second step is very important thing for every class. That is, yeah,
Attendance.
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 Now just 1 minute more to check whether it has been properly downloaded or not, because that part is very important. Somebody is recording now. All these bonus discussions are there. So please don't put it in some public domain. Okay, it will be very embarrassing for me. Okay. Anyway, where is my screen? Okay, now is it there again?
Yes, sir.
Okay, so once we have this calculation, K is equal to B over A square, then we proceed to subdivide this area in suitable elements, infinitesimally small elements. It is here. Now for very small width dx, it is very small. So y value here and y value here, that difference is negligible. Actually, it is a combination of this area, rectangle plus this triangle, or as this x distance has been considered at the middle of this element at half dx, so this height is y, and y dx means area of this rectangle. With that rectangle, this small triangular portion to be added, and this triangular portion, area of this triangular portion to be subtracted, and finally we get that y is equal to dx. So whether you consider the x value at this end or at this end or at the middle is immaterial. So at any location x, we consider the very small width dx, infinitesimally small width dx, and this is the area of the element y dx. Now with that standard element, and whose values are very easily we can find, that value is to determine the location of the centroid of this element. Now x distance of the centroid is definitely x value, but for this element in the calculation integral y dx, so in this expression integral y dA, this y is for that element, and here it is the y value of this curve that divided by 2. That is, this will be half kx square. So in that expression for yc, integral y dA over integral dA, it will be not that kx square, it will be half kx square multiplied by kx square dx. Am I clear? Because you just remember the moment of the weight element wi, or moment of this area, it is corresponding to the load Wi multiplied by location through which force or weight Wi is acting. So this is the location where that element weight Wi is acting. So that part you need to remember carefully. And here in this expression y, it will be not that kx square, it will be half kx square for this element. Along with that, dA is y dx, that is kx square dx, that's fine. Okay. So you finish the calculation and you get this. Now you can check these steps of calculation, because sometime I make some mistake. So please go through this.
Yes, sir, it is fine, sir. My answer also came same. 3 by 4.
This is square. This is the first step to find the value of k. Then for this element, y value for the element will be half kx square. Put it here. It is 3/4 a. And for integral y dA over integral dA, that part we have utilized this value, the denominator, the integration of integral integral y dA, integral dA, that is integral y dx, and this thing is very important. This part. This is area of the parabolic sector. So area of this parabolic sector is integral dA, that is 1/3 AB. Okay. Now that 1/3 AB we are using for the second calculation also. For first calculation, it was this integral x dA, integral x multiplied by y dx, that is kx square dx, etc. That simplification gives us, and integral y dA is half kx square multiplied by that area of the element kx square dx, and it gives 3/10 of b. Now there is one alternative also. That alternative is here. At a distance y, we consider one horizontal element. So area of this element will be length of this element. This is a minus x. That multiplied by dy. So instead of that vertical element, we can consider this is another approach, and for some problem it might be very helpful, useful for you also. So dy multiplied by the length of the rectangle, that is a minus x, and we do the calculation as usual, and you will find the same thing. And what about the location of the individual center of the element? That is half of a plus x. Okay. And you should check this process also, whether you are getting that 3/4 A and 3/10 B, the horizontal range of this sector and vertical range of this sector, which is symmetric. If we complete this thing, it will be symmetric at this vertex about this y-axis. Now, this thing is very important. Area of the parabolic sector, 1/3 AB. Now, can anybody give me the area of an ellipse?
Sir, pi AB.
Pi AB. So how to find that?
Integration.
By integration.
By taking strip.
This equation is
By finding a quarter.
x square over a square plus y square over b square, that's 1. You express y in terms of x or x in terms of y, whatever suitable or convenient for you that you do. And we identify the one quadrant of an ellipse with this equation, either you consider this type of element or we consider the standard this type of element. So again, y dx is the area where y is this one. What about the element? That y value to be used in that integration, integral y dA, it will be half of this value coming from this expression. So the same idea of the previous situation that you can utilize, and you can prove that area is pi AB. Now you just tell me, if we take a circle, now it is looking like ellipse, but truly speaking, we are seeing it from some inclination. Now, if we allow this circle of area pi r square, now you do one thing. We have a bucket, maybe perfectly cylindrical or what it may be, and inside it we have some jelly-like thing, or it's mud. It's not water. So whenever you disturb that water, it will try to come back to this position. Now you take a small plate here of circular shape, and here is one such pin or something like that attached with this, as if it is a piston. And next step, what you do, you allow this circular plate fitted with a handle like thing to move it downward by a distance, suppose h. Now what happens to this thick mud? If there is some provision of spilling out from sides, then what do you get? What is your experience should be? It's very simple. It's not water. It's not coming back to its position here in that way. So normally it will create this kind of empty space. Now what about that shape of that empty space? A cylindrical space whose volume is area of this pi r square, that multiplied by h. That is the simple idea. Now the same thing we can do in this way also. If we consider a container having some muddy material like this, and we have one rectangular plate which is placed in this way, its longer edge matching with the center of this bucket, and we rotate this thing. Here, what about the shape of that mud replaced? After replacing the mud, suppose when you rotate in this way and clockwise, so naturally here also you will get that cylindrical empty space. Now what about the volume of this? If it is R, if it is H, now volume of this mud displaced again due to rotation of this rectangular cardboard like or a metal plate like thing, it is rotated about this axis, which is the center of this container. Here also it gives us that empty space. What about this volume? So we are replacing that same volume of mud, either plunging this circular plate through a depth of h of radius r, or rotating a rectangular plate about one of its longer side, whose longer length of this side is h and width of this plate is r. Here also it generates this empty volume, the mud displaced, that is also pi r square h. Okay, that is the idea. So before going to our next part, we remember that idea and simply we think about this axis, and we consider a small element dA and allow it to rotate about this axis. Suppose it is y axis. Okay, now it will generate a volume. Now what about the volume? If
Sir, pi r square dA. Pi x square
pi
dA.
x square multiplied by dA. Of course, the volume generated by this small rectangular element dA, if it travels.
Sir, 2 pi x dA, sir.
Thank you. So I should not believe any of your suggestion blindly. So if it travels by twice pi x, and in that case, this volume will not be exactly same, but for infinitesimal small area dA, we can neglect, and for some bigger area, this small calculation can be utilized. So actually it will be like this. Okay, now at any location, this is the shape of the cross section, but for very small area element dA, it will be twice pi x multiplied by dA, and that is very important clue. Similarly, if we take a small length dl and allow it to rotate about this axis, which is at a distance x, then what about the effect of this rotation of a small length dl?
We'll get some surface, sir.
It will create some surface, and area of the surface is twice pi x multiplied by dl. So that is the area, and this is the volume. So the area generated by a small length dl about one axis is the distance traveled by that small element multiplied by the length of the element, length of the plane curve or something like that. And volume generated is product of the area of the element with the distance traveled by that small area during this rotation. And the very small idea, very simple idea, but enormous application, so many things. You just think about the volume generated by one semicircular sector. Now, which volume it will generate? It will generate sphere.
Yes, sir.
Okay. So it will be half pi r square, that multiplied by twice pi multiplied by 4r over 3 pi. What about that? 4/3 pi r cube. But where from we get this thing? We are getting the same thing from that previous idea that if we consider a small area element dA. Okay, sorry, this is already 10. Your next class.
Sir, we have,
Yes.
Sir.
Just one
We have
second.
another.
So area generated by this small element dA will be twice pi x multiplied by dA, and total volume will be integral twice pi x dA. This is twice pi multiplied by integral x dA. That is twice pi multiplied by a multiplied by xc here. This is twice pi xc multiplied by a, area of this full plane figure, that multiplied by the distance traveled by the centroid. So please go through the book and just finish this thing. One is this, other is twice pi xc multiplied by L, area generated by a plane curve of length L equal.
Sir, you are muted.
Now these two theorems are there. In some book you will find theorems of Pappus, in some book you will find theorems of Pappus and Gouldinus, because separately and simultaneously both of them have done these things. So they have theorems, one for area, theorem 2 for volume. Okay, so please complete this part through any book, and in our next class we will discuss in detail if you have any problem. But for today, let us close here because we have already the time of starting of your next class. Okay, please. Thank you.
Thank you, sir.